Top of the morning, people. Has anyone here ordered an example of torque with an extra incline force? Anybody? We have one ready here right away. Better get it while it's hot. So, we already figured out what torque actually is. If you are still clueless, it's better to look at our video on torque first. Today, we're going to look at an example containing inclined forces. Let's imagine that we have a diver who is about to jump from the 10-meter tower. The diver exerts an inclined force onto the side of the diving board, which makes sense because he would just land on the board again if he were to jump straight up in the air. The inclined force is the result of an upwards jump and a lateral forward force. After all, our diving buddy would like to end up in the water. What are the values known to us already? We know the length of the board, and we know the force exerted by the diver onto the side of the board. Ah, right. Almost forgot. We also know the angle by which the force is inclined relative to the axis on the board. Now, we want to figure out the torque that is exerted onto the left end of the board. That's point A. The formula for torque is quite easy. Moment M equals the length L times the force F. Now, we will calculate the force in two different ways. Then, you people can pick the method you prefer. As you will see, they both have their advantages. Exactly the same as in the case of the PQ and the ABC formula. Jump on whichever train you want because they will both get you to the same station. Let's start with the component method. We jumped on the component method train, which means that we will adapt the force measurements to find the moment using the defined length of the board. What do we mean by adapt the force measurement? Well, it's as simple as decomposing the force, splitting it up into its x and y components. Let's do so together, step by step. First, let's have a detailed look at the force. We make it easier for ourselves by adding the x and y axes at the point where the force is exerted. Now, we want to separate the force into its x and y components. This is easy. We just use sine and cosine functions. Let's rearrange the forces like this, and it's much easier to see. The forces now form a right-angled triangle. The hypotenuse of the force is simply the force we already gave you, so 800 Newton. The y component, our Fy, is the opposite leg of alpha, which gives us the sine of alpha equals Fy divided by F. If we solve for Fy and insert 50 degrees for alpha and 800 Newton for F, we get an Fy value of 612.84 Newton. Well, that was easy. Let's repeat all that mumbo-jumbo for Fx. Our starting formula is cosine of alpha equals Fx divided by F. Solving for F and using the correct values, this gives us an Fx of 514.23 Newton. Well, the hard part's behind us now. The torque we're already trying to determine is simply the sum total of individual force moments. So the moment exerted by Fx plus the moment of Fy equals our total moment. This method comes with the great advantage that the distance of Fy equals the length of the board. With a board length of 5 meters, this gives us a moment of a little over 3,000 Newton meters. Now, we need to pay attention to the sign. The moment turns in a clockwise direction, which means that my is assigned a minus. So you think that was easy? Just have a look at what happened to our mx. Let's look at the sketch again. The distance of Fy to A was the length of the board, but what is the distance from Fx to A? Because we're already looking for the perpendicular distance of the force, we can easily recognize that the vertical distance of the force in this case is simply 0. If the force were located somewhere else, here for example, we could determine its distance from A, but that's not the case. This makes it super easy because this gives us an Fx moment of 0, and our total moment is the same as our y moment. So you're thinking that we could have just forgone all the calculations for Fx? Well, you're correct. Actually, we only needed to determine Fy to be able to determine the total torque. In these cases, the component method is very convenient. However, because we want to give you the full picture, let's have a look at the second method as well. With this method, we won't split up the force into its various components. We're just going to try and determine the actual perpendicular distance. So, at its core, we're dealing with geometry. First, we add a few artificial lines to help us. We first need the line of action of force F. And then, we need the perpendicular distance of point A to the line of action of F. Let's call this distance S, and it's vital that it's vertical relative to the line of action of F. So when using this method, we're basically just trying to determine S. Using various simple laws of trigonometry, we can recognize that the angle alpha should form part of the right angle triangle. Now, we know the hypotenuse or length of the board and the angle of alpha. So we can find s by working out the sine of alpha. In this case, the sine of alpha equals s divided by the length of the board. Solving for s with an alpha of 50 degrees and a board length of 50 meters, we get a length for s of 3.83 meters. Now that we actually have the perpendicular distance of force F, we can insert all that jazz into the moment formula. Would anyone like to take a guess at the result? That's easy, of course. The same result as with the first method, which is 3064.2 Newton meters. Here too, the force F has a clockwise rotation around point A, which means that we need to assign a minus sign. Awesome! Now we've had a detailed look at both methods. At the beginning, you should try and use both methods, as each comes with its own advantages. It can, for example, be very convenient to split up a force into its components when one of the components then runs through the point of reference and the distance becomes 0. However, if neither component crosses the moment's point of reference, this method might just result in more laborious calculations. The same applies to the second method. With more complex geometries, it's easier to make mistakes. However, if you know the correct distances, you need not worry about that. As always, practice makes perfect. Alright, I hope that gave you people a clear idea of how to approach challenges like this one.